All right, let's go ahead and start with our first section of the term. So for this video, we're covering 1.1, what is a graph? We're going to be introduced to what is a graph, some applications, and more importantly, some really fundamental concepts and definitions that we're actually going to be using for the entire term. So let's go ahead and start with the birthplace or the origin of graph theory. So here I have a map of Koenigsberg, and notice here that I have it titled the Koenigsberg Bridge Problem. So if I go ahead and look at this map right here, notice that for this city of Koenigsberg, it's naturally split into 4 sections. I have, well, this upper northern part of my city, this middle island, and then this bottom portion, and then this part on the right. So again, I have these 4 natural subdivisions of my city. And then all of these subdivision or land masses are connected by these 7 bridges. So the people of Koenigsberg wondered, if I started at some random landmass, for convenience, let's just say I started at the top up here in the northern portion of the city, would it be possible to tour the entire city while crossing each bridge exactly once and only once? So I'm starting at the very northern portion and I'm trying to hit every single bridge exactly once. And I don't want to repeat any of my bridges. So as it turns out, based off our city model, it's actually impossible for us to do this. And again, this is actually what we commonly refer to as where graph theory really sort of started. So if I were to simplify this map, let's go ahead and pull this up. So here I have the same map, just a little bit with less detail, none of the buildings or anything like that. And notice that I went ahead and I labeled my 4 land masses as A, B, C, and D. So if I wanted to look at an even simpler picture of this, I can go ahead and represent each portion of my landmass as a vertex or a dot. And then if these land masses have a bridge connecting them, I can go ahead and draw a line between the two. So for example, here between B and D, there's a bridge connecting them directly. So I can draw a line between the two. I can do the same thing for A and D. For A and D, there's a bridge connecting them, as I can see right here. And then I can draw a line connecting the two. And I can do the same for the remaining bridges. One thing that I want to point out before I go further is notice between A and B. Between A and B, there were 2 bridges connecting the two. So I had to draw 2 separate lines. Now I'm going to go ahead and clean up this picture even a bit further, so that it's a little bit easier for us to look at. I can redraw this to look like my graph over here. So this is a little bit cleaner and easier for us to look at. And notice that I went ahead and I labeled my edges as E1, E2, E3, E4, and so on. So whenever I'm looking at this, we just made a graph. So starting off with a vertex. Here I can call my dots or my nodes. More formally, I call these to be my vertices. And then these lines connecting the two, I call them my edges. So I have my vertices and my edges. So now we can go ahead and now more formally define what does it mean to be a graph. So our first definition for the entire term. A graph is an ordered pair, V, E, where V is my vertex set, so my set of dots if you want to word it that way. And then my edge set. Here I'm going to denote E for edge. These are my set of lines, or more formally my edges in my graph. So whenever I'm looking at a graph, some other definitions that we're going to bring up. If I have a pair of vertices, let's say U and V, if they're connected by an edge, then we can say that U and V are adjacent to each other. Or you might also hear me say that they're neighbors. U and V are neighbors. And then if we do have an edge connecting the two, we can also write UV is an edge of E, or belongs to the edge set E. All right, and then what other definition I'll put in here? If I do have an edge with endpoints U and V, then we say that the edge is incident to the vertices u and v. So a lot of times you're going to hear me say the edge uv has incident vertices u and v. So if I go ahead and pull up that same graph I had earlier, then for this graph, my vertex set v is the set of all labeled vertices, or in this case, A, B, C, and D. So I have my vertex set. And then my edge set is, well, E1, E2, all the way up to E7. So I have my edge set. Again, this is how we formally define a graph. Let's go ahead and continue looking at some more definitions. For this section, we're going to be covering a lot of definitions, so this particular video may be a bit longer than our usual one, but it's largely definitions that we're looking at. So for our next definition, notice that I went ahead and mentioned in that previous slide that A and B had two bridges connecting them, or two edges. Whenever we have this scenario, we actually call E1 and E2 to be a multiple edge. So multiple edges are distinct edges having the same pair of endpoints. That is, E1 and E2, both of them have incident vertices of A and B. The next thing I'm going to mention is, well, let's look at A. Is it possible that I have an edge that starts at A and also ends at A, such as what I have right here? So if I draw a line that starts and ends at the same spot, we actually call this a loop. So a loop is an edge where the endpoints are equal. Again, I start and end at the same spot. So a lot of times, one thing that we're going to be interested in is this thing called a simple graph. A simple graph is a graph that has no loops or no multiple edges. And no multiple edges. So a lot of times in our class, we're going to be talking more about the simple graphs rather than the multiple edge graph or loop graphs. So we've defined multiple edges and loops. Let's go ahead and also define finite. A graph is finite if I have a finite list of vertices and edges. And then if I have a graph that has no vertices and no edges, I call that the null graph. In other words, I have a graph where there's absolutely nothing. So again, unless I explicitly state it, we're going to assume that everything that we're working with for this term are non-empty and finite graphs. So let's go ahead and pull up another example of where we might use a graph. So here I'm going to pull up a picture with some major cities in the United States. I have San Francisco, LA, Denver, Chicago, Detroit, New York, and Washington. So what might this graph represent? I may say, for example, in these major cities, I may have built some data centers. And then if I have an edge connecting these two cities, I may say that these data centers are connected by some type of network. So for example, the data centers in San Francisco and LA, they may be connected. And then also notice that I have these little loops here where San Francisco goes to itself. And I actually have it for each city. And a little bit of a real world application, I may say that these data centers have a loop connecting to itself as a sort of data or self-diagnostic. So this is just a very quick way that we can also look at an application of the graphs that we're working with. All right, so some more definitions. I know we have a lot of definitions here if you're looking at the notes right now. So let's say I have a loopless graph with some vertices and edges. Again, I'm just discussing this very broadly. I have some number of vertices, some number of edges. One thing that we might be interested in is called the adjacency matrix. Remember, what does it mean to be adjacent? That means I have two vertices that are connected to each other with an edge. So the adjacency matrix A of G, this is an n by n matrix where the entry I, j is the number of edges in G that have the endpoints vi and vj. So this definition is really formal. If this looks a little bit confusing to you, don't worry, I am going to do an example in just a moment where it's going to be a little bit more clear. The next thing I'm going to introduce is an incident matrix. Remember, whenever I discussed an edge, we talked about its incident vertices. This is an n by m matrix, in which the entry m sub I comma j is 1 if vi is an endpoint of ej and otherwise is 0. Again, this is a very formal definition. You're going to see what I mean a little bit more whenever we do our example. So since we've been working with that graph from Koenigsberg, let me go ahead and bring up that picture again. So here I have that same graph, and let's build our adjacency matrix. Well, remember the adjacency matrix is an n by n matrix. That is the number of vertices times the number of vertices. So here I have 4 vertices, A, B, C, and D. So I should be dealing with a 4 by 4 matrix. So let's go ahead and set this up. So here I set up my matrix, and notice I labeled each row and column with A, B, C, D. So in my first entry right here, where A and A look like they intersect, if there is an edge from A to A, then I put down a 1. If there is no edge from A to A, I put a 0. So I'm going to go over to A, and there's no edge that starts at A and ends at A. That is, there's no loop for A. So I should be putting a 0 for my first spot. Now for my second spot right here, next to it to the right, I'm looking at the intersection from A to B. Again, if A and B share an edge, that is, if they're neighbors, I'm going to put down a 1. But if they're not neighbors, then I'm going to put down a 0. And I might have to put more numbers if there's multiple edges. So let's look at A and B. So looking at A and B, I have 1 edge, I have 2 edges. So I have 2 edges connecting them. That means in this spot, I should put a 2. And then I'm going to go down the line. For A and C, if I go to A and I look at C, these are not directly connected. So I'm going to go ahead and put a 0 there. Same thing for A and D. If I do A and D, they're connected by a single edge. That means I'm going to go ahead and put a 1 down. And now I can do the same thing for the rest of these entries. A and B, again, we did this earlier. A and B have 2 edges connecting them, so I'm going to put a 2 there. B and B, there's no edge that goes from B and then ends at B, so I'm going to put a 0 there. For B and C, we have 2 edges connecting them, so I'm going to put a 2 here. And for B and D, there's 1 edge connecting them. So I have these first 2 rows. As you can imagine, the last 2 rows, we're going to do the same thing. For the sake of not just going through repeating ourselves, here I've gone ahead and filled out the entire adjacency matrix. One thing that I want you to notice about this adjacency matrix is that we also have this sort of diagonal symmetry. If I were to fold this along this diagonal, going from the top left to the bottom right, it looks like I just copied my values down. So this is our adjacency matrix. I'm just able to look at my graph and create this matrix from that graph based on whether I have a neighbor or not, and how many edges to be exact. Now let's go ahead and look at our incidence matrix. So for our incidence matrix, I'm going to go ahead and do the setup first. My incidence matrix is denoted with an M of G, where for this first column here, I have it labeled A, B, C, D. And then I have it from here, E1, E2, E3, all the way up to E7. So I have 4 vertices and 7 edges. So I have a 4 by 7 matrix. So I'm going to go down for the first column, first row. It looks like this intersection between E1 and A. If I look at the edge E1, does E1 connect to A? Well, if I look at my graph, E1, yes, is connected to A. So that means I'm going to put a 1 down. Continuing down the line for E2, does E2 connect to A. That is E2 incident to A. Very quickly, I look at E2, and it's connected to A, so I'm going to put a 1 there. And then the same thing for E3. E3 is definitely connected to A, so I can put a 1 for my next spot. And then for the remaining spots, E4, 5, 6, 7, I can see the only edges connected to A are E1, E2, E3. So the rest of these should be 0, actually. So that's how we fill out this first row. Alternatively, you could have also done by column, is whatever way. You should get the same solution in the long run. So again, just for the sake of not having to repeat ourselves over and over again, I'm going to go ahead and fill out this table immediately. So just real quick, E1. E1 is connected to A and B, so I am expecting a 1 at A and B and a 0 for the remainder. And then we can go column by column or row by row, depending on how you want to fill this out. But here we have our incidence matrix of my graph G. Now let's go ahead and talk about relationships between one graph to another. So for this next definition, let's talk about isomorphism. If I have two separate graphs, an isomorphism from G to H, I'm going to use some formal language here, is a bijection that maps the vertices of G to the vertices of H, and the edges of G to the edges of H, such that each edge in G with endpoints U and V is mapped to an edge in H with endpoints in F of U and F of V. And if I can find such an isomorphism from G to H, we can say that these two graphs are isomorphic to each other. And rewrite this little notation right here. It looks like an equal sign with this squiggly line above it. So what does this mean in layman terms? In other words, if I say two graphs are isomorphic, I'm saying that these graphs are essentially the same graph. Maybe I labeled them a little bit differently, but in the end, they're the same graph, or more accurately, I would say that they're equivalent to each other. So here I have an example, G and H. So if I look at these two graphs, I might ask, are these isomorphic to each other? Are these the exact same graph? Because I'm saying, well, let's see, G has a triangle, H has a triangle, and both of them have this single line coming out. So if I look at this graph G, what if I just relabel this some type of way? What if I relabel this A with a 2, the C with a 4, this B with a 1, and this D with a 3? Well, if I relabel this G in this way, I get the exact same graph that I have here. For example, here 4 is connected to 3 vertices. Two of them are on a triangle, one of them is by themselves. I have the same thing going on over here for 4. It's connected to 2 vertices on a triangle and 1 vertex that's by itself. And actually, if I want to define my bijection, I can say A and 2 are essentially equivalent, C and 4 are equivalent, B and 1, and D and 3 are equivalent to each other. So here I might say G and H are in fact isomorphic to each other. So we have our isomorphism. Next thing I'm going to talk about is subgraphs. A subgraph of a graph G is a graph H such that my graph H has either the same vertices or less vertices, and the edges in H are a subset of the edges of G. If H is a subgraph of G, we use a special notation. H is a subset of G, or we might say G contains a copy of H. If H is not a subgraph, then we can just say that G is H-free. So once again, we're going to look at this in terms of an example. Here I've gone ahead and defined two graphs, H and G. H just looks like 4 vertices that are connected in a square shape, and G is this bigger graph. So if H is a subgraph of G, then I'm saying that I can find something that's like a square in my graph G. So in fact, if I highlight these 4 edges and these 4 vertices, I can see that what I've highlighted here is actually the same thing as what I have here on the left. That means that H is a subgraph of G in my example. Hence, I can write this here. So I have the definition of a subgraph. Again, more definitions. Again, you're probably sick of me saying more definitions, but a lot for us to start off with for the term. Next definition, I want to talk about this thing called a complete graph. A complete graph, I'm going to use this notation K sub n. So a complete graph Kn has n vertices, and sometimes you might hear me call it an n-clique. This is a simple graph where all the vertices are pairwise adjacent. Or in other words, this means that I have a graph with n vertices and every possible edge exists, while it's still being a simple graph. Now, if I'm not necessarily talking about a complete graph, I might also talk about the clique number. The clique number, omega of G, of a graph G is the maximum size of a clique subgraph in G. Again, these are more of our formal definitions. Let's go ahead and look at an example of this. So here I've got three graphs, starting with the one on the far left. Here I have, 1, 2, 3 vertices. If I look at these three vertices, every possible edge there exists. If I look at 2, it's connected to every other vertex. If I look at 1, it's connected to every other one. If I look at 3, it's connected to the other 2 vertices. So, since every edge exists, and it's still simple, and since I have 3 vertices, then I call this the complete graph K3, or in other words, the 3-clique. Looking at this one over here in the middle graph, I have 1, 2, 3, 4 vertices, and each vertex is connected to all the other vertices. Hence here I have the K4 graph, that is the 4-clique. Now for this last graph, I have 1, 2, 3, 4, 5, 6. I have 6 vertices, but clearly I'm missing some edges. For example, this middle vertex here and this one on the bottom left, there's no edge connecting it, so I don't have a complete graph here. So I might be interested in what's the clique number. In other words, what's the biggest clique subgraph I have in this last one here? Well, the first thing that I'm going to note here is I clearly have a K3 subgraph. I've got a triangle. This tells me that K3 is a subgraph of G. I could have also used this triangle on the far right. Well, since K3 is a subgraph, that means my clique number is at least 3. And I'm actually going to go ahead and prove very quickly that it is actually in fact equal to 3. If I have a K4 subgraph, then my clique number will be at least 4. But if I do not have a K4 subgraph, then my clique number is less than 4. Well, very quickly I can tell that I'm not going to have a K4 subgraph. If I look at this K3, if I try to add in another vertex, I'm going to be missing an edge one way or another. So there's no way I can have a K4 subgraph. That tells me that K4 is not a subgraph, which then tells me that my clique number, omega of G, has to be smaller than 4. Or in other words, less than or equal than 3. So whenever I put these two together, the only way for both of these to be true, bigger than or equal to 3, or less than and equal to 3, this means, let me move myself, that my clique number has to be exactly 3. So this is a little bit about how we find the clique number. And then there will be some examples in the homework for you to practice. So moving from here, let's go ahead and talk about the union of a graph. So next, talking about the union of a graph, let's say I have a bunch of smaller graphs, G1, G2, all the way up to GK. The union would be G1, union G2, union so on, all the way up until my last graph, GK. This is a simple graph with a vertex set, the union of all the vertices, and the edge set the union of all the edges. Again, this is a really formal definition. If I look at this example right here, I have G1 and G2. What if I want the union of G1 and G2? Well, if I look at this union, the first thing I'm going to note is notice that both of these graphs have A and B in them. I have A and B here on the left, and I have A and B on the right. If I want the union of these two graphs, what I usually like doing first is I like listing out all the vertices. Here I have the vertices A, B, C, D, and E. So I went ahead and put them all out. Well, for my definition of a union, the edges is basically all the edges that came from G1 and all the edges that came from G2. So from G1, I had this triangle ABC. So in my union, I'm going to do the same thing. I have the triangle ABC. In G2, I had the square ABDE. So I'm going to do the same thing for the union. I'm going to put the triangle ABD and E. Notice that even though both of them had the edge AB in G1 and G2, I did not put down a multiple edge. That's because by definition, my union should be simple, meaning I don't want any multiple edges. So here I have the union G1 union G2. So this is our union. Now going ahead looking for next thing I'm going to introduce is a complement graph. So a complement, here I'm using this notation G bar. If I take the complement of a simple graph, this means that the complement has the same vertices, but it has, I'm going to use the word, the opposite edges. And a graph is self-complementary if the complement and itself are the same. So once again, being a little bit more informal, if I look at this example, I have A, B, C, D. This is my graph G. My complement has the same vertices and the opposite edges, meaning if the edge was not in my original graph, then the edge should be in my new graph. So if I look at my original graph, there's no edge between A and B. So in my complement, there needs to be an edge between A and B. Similarly, B and D is not in there. So BD should be an edge in my complement. And then the same thing for BC. BC is not in here, so BC should be in my new graph. AC is in my original graph, so AC is not in my complement graph. Same thing for AD and DC. So here I have my complement graph. So we have a graph G and its complement. The vertices are the same, but the edges are opposite from what we originally had. Next thing I'm going to talk about is this concept of independence. So if I have an independent set in a graph, this is a group of vertices that are not adjacent. In other words, an independent set is a group of vertices that are not directly connected to each other. So whenever I talk about this idea of independence, we also talk about being maximal and maximum. So an independent set is maximal if you cannot add any more vertices to it. In other words, it's not a subset of any other independent set. If you add another vertex to your maximal independent set, then it's no longer independent. On the other hand, maximum, notice that these are two different definitions. Maximum independent set is the biggest possible independent set that you have in a graph. So if I have a maximum independent set, whatever size it is, that is actually what we call the independence number, alpha of G. So looking at an example, I really want to emphasize the difference between maximal and maximum. So here I have the same graph, but I circled different vertices each time. For this first one on the left, I circled this one on the top left and this one in the bottom middle. So first off, this is definitely independent. The vertices I've circled are not connected to each other. So I'm independent. That's really nice. Am I maximal? Again, maximal means if I try to add another vertex to my group, is it still independent? Let's see. I can't add this vertex on the bottom left because it's directly connected to one of these vertices. I can't add this one because it's connected to actually both of them. I can't add this one on the top right because it's connected to this vertex. And I can't add this vertex down here on the bottom right either because it's connected to here. So that means that this set that I've circled is maximal. I can't add any more vertices in. Now we don't know if it's maximum yet. But here, as it turns out, it will be independent and maximal, but not maximum. The reason it's not maximum is, well, for this example on the right, if I take these three instead, this is definitely still independent. None of these three are directly connected to each other. And I can't add any more vertices, so it's maximal. And as it turns out, it is maximum. So it's independent, maximal, and maximum. And since the maximum independent set has size 3, this means my independence number, alpha of g, is equal to 3. So we have this here. So just as a very brief idea on why is this equal to 3, let's go ahead and just introduce this proposition. If I have this graph, why is it equal to 3 exactly? How do I know that this is the biggest possible maximum independent set? So based off this picture, I can already tell you that my independence number has to be bigger than 3. Because, remember, this means the size of my biggest independent set. So right here, this is an independent set. If I have a bigger independent set, it has to be either 3 or bigger. So I know my lower bound is 3. So if I want to show that this is equal to 3, then I should be showing that this number should be less than or equal than 3. If this is true, to make this true, then I have to make it equal to 3. This is equivalent to saying that I don't have any independent set of size 4. And as it turns out, this is something that you can check on your own time as well. There is no independent set of size 4. Since C, E, and F, these three, are on a 3 clique, that means I can only select one vertex from here. For the same idea, since B, C, and E lie on a triangle, then I can only choose one vertex from here. Thus, from these 4 on the right, B, C, E, F, I can only choose at most 2 vertices and still be independent. Lastly, A and D, I can only choose one of them. Thus, if I take 1 from A and D and 2 from the remaining 4, that means every independent set only has at most 3 vertices. Finishing up my proof. So this is a very quick proof. I know I went through this fairly quickly. I do recommend that you look over this proof and see why this is true. All right, so moving on, the next 2 definitions that I want to cover are being bipartite or T-partite. So a graph is bipartite if I can write the vertex sets into a natural partition, X and Y, such that X and Y don't share any vertices, and that they're independent. If this is true, then we call it an XY bigraph. So in other words, I have 2 independent sets. T-partite, we're actually using the exact same idea. So instead of 2 independent sets, I can have as many as I want, up to T. So again, just as an example, here I have a graph. X and Y are my vertex sets. Notice that both of these sets are independent. So in X, none of these are connected to each other. Y, none of these are connected to each other. So this graph I have here can be considered bipartite or a bigraph. So I have my bipartite, and you can imagine if I added a third set and more vertices, I can have a three-partite set. So here we have the definition of bipartite. And then our very last definition for this section, I want to talk about a complete bipartite set. So remember before we talked about a complete graph like K4 meant I have 4 vertices and all 4 were connected to each other. So for a complete bipartite graph, this is a bipartite graph such that 2 vertices are connected to each other if and only if they're in 2 different sets. So for example, here I have a complete bipartite graph, K3, 2. On the left, I have 3 vertices. On the right, I have 2 vertices. So whenever I look at this complete bipartite graph, from these three are connected to every single vertex on the right. And on the right, both of these vertices are connected to every vertex on the left. So this is a subgraph of my complete graph. So here, clearly on the left, these 3 are independent, and these 2 on the right are independent. So here we have a complete bipartite graph. All right, so that is our first section. I know this video is a little bit longer, but it's primarily because we had a lot of definitions and a lot of things for us to look at. This will serve as a great foundation for anything that we talk about for the rest of the term. Besides that, good luck, and see you in the next video.